Beneath the quiet vastness of the night sky, a paradox unfolds. Every star shimmering above is a messenger from another time. Some have already burned out, collapsing into silence long before their light ever reached this fragile world. Others endure still, but even they are not what they appear to be. What we see in the heavens is never the present, it is always the past. Space does not simply surround us. It is an ocean of memory, carrying echoes across gulfs so immense that no imagination can truly measure them. To look outward is to look backward. Each photon that strikes the human eye began its journey long before memory, long before civilization. The faint glimmer of Andromeda, the nearest great galaxy, departed 2 million years ago, when no human being yet walked the earth. The pale wash of light from distant quasars began its voyage before our sun was born, when the Milky Way itself was still young. The sky above is not a stage of living stars, but an archive in ancient library written in light. Astronomy, then, is not simply the study of objects across vast distances. It is the science of time itself. Telescopes are not just magnifying glasses into space. They are instruments of archaeology, tunneling backward into the history of everything that has ever existed. Each observation is a journey into deeper strata of the cosmos, as though the universe were made of layered ruins, galaxies fossilized in their youth, nebulae frozen in the act of becoming, light stretched and thinned as it drifts through the unyielding current of expansion. Yet there is a deeper enigma at work, one more unsettling. Space is not simply the theater where time's events unfold. It may be the very machine that carries us through time itself. To cross space is to cross hours and centuries. To follow light is to trespass into eras long vanished. Even in stillness, this earth races through a current of space-time, dragging every living being along the single direction of time's arrow dot. And so the question rises, urgent and inexhaustible, is the universe itself the ultimate time travel device, not crafted by engineers, not imagined by storytellers, but etched into the very laws of physics? If so, then every glance into the night sky is more than wonderful. It is participation in a cosmic journey that no one can escape, a voyage where past, present, and future blur into the great silence of the stars. In the ancient world, before the first telescope turned toward the sky, time was not yet measured by equations, but by rhythm. The Babylonians charted the cycles of planets and stars, believing the heavens to be a clockwork of repeating patterns. The Greeks debated whether time was a river flowing endlessly forward, or a wheel turning endlessly upon itself. For Augustine, time was a tension between memory and anticipation, a human condition tethered to eternity. In these reflections, time was something lived and felt mystical, elusive, inseparable from the rise and fall of civilizations. Yet even then, an intuition lingered. The sky above was not merely distance, but history. Centuries later, Galileo watched pendulums swing and objects fall, searching for order in motion. In his experiments, time began to take form as a measurable quantity, a silent partner to movement itself. Isaac Newton gave that partner its ultimate identity: absolute time, absolute space. In his vision, the universe was a vast stage upon which matter performed its dance, every second ticked off by a perfect cosmic clock, untouchable, the same for gods and men alike. It was a reassuring vision, one that placed human understanding within an eternal framework. Time, in Newton's universe, was steady, impartial, inevitable, but this certainty was not to last. In 1905, a young patent clerk named Albert Einstein proposed something profoundly unsettling. Time, he argued, was not universal. It stretched, contracted, and bent in response to motion. It was not a separate entity from space, but inseparably fused into a four-dimensional fabric, space-time. Simultaneity was an illusion, and events once thought absolute were revealed as relative, dependent on the observer's state of motion. What Newton called the steady beat of the cosmic clock was revealed to be a malleable rhythm, distorted by velocity and gravity alike. Beneath this revolution lay a simple but staggering truth. The speed of light is finite, roughly 300,000 kilometers each, seconds swift enough to circle the Earth 7 times in a heartbeat, yet not infinite. This limit transformed human perception. To see the sun was to see it not as it was, but as it had been 8 minutes earlier. To watch a supernova in another galaxy was to witness an explosion that occurred millions of years in the past. Every glimpse of the universe was already a form of time travel, bound by light's relentless pace. Then, in 1929, Edwin Hubble peered into the sky and discovered another layer to the puzzle. Galaxies were not stationary lanterns fixed in a dome, they were rushing outward, carried on the expansion of the universe itself. The deeper one looked, the further back in time one reached, until the cosmos itself appeared to recede into its own origin. The telescope was no longer an instrument of simple magnification. It had become a vessel for temporal exploration, its lenses opening windows onto eras unreachable by any other means. The realization spread slowly, but irrevocably. The night sky was not a mirror of the present. It was an archive of everything that had ever been. Every glimmer was an artifact, a fossil of photons preserving the memory of stars, galaxies, and collisions across billions of years. The astronomers who lifted their eyes to the heavens were no longer just measuring space. They were touching the fabric of time itself, uncovering the first hints that the universe was not merely a stage 4 times unfolding, but perhaps the very machine that carried it forward. When Einstein's vision of space-time emerged, it fell upon the scientific world like a quiet earthquake. For centuries, scholars had lived under the comforting weight of Newton's absolute time as a universal heartbeat, space as the stage upon which all things played their part. But suddenly, the stage itself was alive, bending and warping, carrying time with it. The steady rhythm of the universe was shattered, replaced with a revelation that time was not singular, but fractured, woven differently for every observer in motion. The shock was profound. Physicists who had built careers upon the certainty of an eternal now found themselves staring at equations that seemed to deny such a concept altogether. Einstein's special relativity spoke of simultaneity as an illusion. 2 events that appeared to occur at the same instant for one observer might unfold at different times for another. There was no single, objective presence stretching across the universe only, shifting layers of experience, each bound to its own perspective of motion and light. This realization unsettled not only the scientific imagination, but the human one. To think that there is no universal now was to undermine one of the deepest instincts of existence. The mind insists upon the present as real and indivisible, yet the universe revealed something colder, stranger. Time was not a river flowing the same for all, but a fabric stretched and folded by speed and gravity. The philosopher's ancient river of time was replaced with a 4-dimensional continuum in which past, present, and future existed as coordinates, each bound together in silence. Not all welcomed this vision. Some dismissed it as mathematical trickery, too alien to reconcile with lived experience. The thought that a clock on a speeding train would tick slower than one at rest seemed an affront to common sense. Yet the mathematics was relentless, and experiments soon followed. In laboratories and in particle accelerators, in the ticking of atomic clocks flown aboard aircraft, the distortions of time revealed themselves again and again, undeniable. The human sense of the present dissolved, replaced by a cosmos where every vantage point carries its own timeline. For astronomers, this understanding transformed their instruments. A telescope was no longer simply an eye, extended outward became a time machine, pulling the gaze into the depths of history. When they studied the Andromeda galaxy, they were not seeing it as it is, but as it was 2 million years ago. To look at the faint glow of a quasar was to witness a lighthouse shining from a universe billions of years younger. Distance became indistinguishable from age, and the act of observation itself became an act of archaeology. And so, beneath the immensity of the sky, a new humility emerged. Humanity was forced to accept that it never perceives the universe as it is, only as it was. The heavens ceased to be a mirror of the present and became an archive of vanished moments, written in photons and stretched across the black ocean of space-time. In this recognition lay both wonder and sorrow, the realization that to look outward is always to peer into memory, that the stars themselves are letters from the dead, carried faithfully across the silence of eternity. The debate over Einstein's reimagining of time spilled far beyond mathematics. It was not only a question of physics, but of philosophy, of existence itself. If there is no universal present, then the cherished line between what is and what was begins to blur. The philosopher Henry Bergson clashed with Einstein directly, insisting that the flow of lived time could not be reduced to coordinates in geometry. For Bergson, time was inseparable from consciousness, from memory and anticipation. Einstein, unmoved, maintained that physics dealt with what could be measured, not with the illusions of perception. Their public dispute in 1922 echoed through both science and philosophy, a clash of worldviews that revealed the depth of unease stirred by relativity. For those who accepted Einstein's framework, the consequences were staggering. No longer could the universe be imagined as a stage set at one moment in cosmic history. Instead, every observer became the bearer of their own time. A person standing still, a spacecraft hurtling through the void. A photon racing at light speed inhabited a distinct timeline. Each carried a different rhythm. The notion of simultaneity, once taken for granted, dissolved into relativity. This idea was soon tested in ways that transcended theory. In 1938, experiments using particle decay revealed the first signs of time dilation. Muons, unstable particles born high in the atmosphere, should have decayed long before reaching the Earth's surface. Yet they arrived in abundance. Their internal clocks, moving at near light speed, ticked more slowly than those on Earth. Nature itself confirmed what equations had predicted. Time could stretch, flex, and warp depending on motion. Such discoveries did more than challenge physics. They unsettled the human relationship with time. For millennia, time had been the most democratic of forces. It touched every being equally, its passage the same for kings and shepherds, stars and oceans. But relativity fractured this equality. Two twins, one earthbound and the other voyaging at near light speed, would return to find themselves no longer the same age. The simple bond of shared time was severed by motion itself. To the wider public, these revelations were disorienting, and yet strangely poetic. Newspapers of the early 20th century reported on relativity with a mixture of awe and disbelief, describing a universe where clocks could disagree, where rulers shrank, where nothing was fixed. For some, it sounded absurd, a mathematical fantasy untethered from reality. For others, it was exhilarating, a glimpse into a cosmos stranger than any myth. But perhaps the most profound shift came not from laboratories, but from the telescopes. The acceptance of finite light speed, coupled with the relativity of time, transformed the very act of stargazing. Astronomers began to understand that their instruments were not recording the present state of the heavens, but layered pages of history. Each increase in telescope power did not simply enlarge vision, it extended it deeper into the past. A telescope was a time ship, its glass and mirrors tuned to ancient signals, catching the whispers of galaxies long since altered or destroyed. The Hubble telescope's predecessors had already hinted at this, but it was Edwin Hubble's own work that forced the point with undeniable clarity. By showing that galaxies were receding from one another, he demonstrated that the further one looked, the further back in time one reached. Space was not static. It was a chronicle in motion. Every deep sky photograph was a layered palimpsest, a record of ages stacked upon ages, each photon a messenger from a vanished moment. Such knowledge struck at the heart of human perception. The eyes, long trusted to reveal the present, were revealed as unreliable narrators. The stars overhead were not companions in the now, but memories projected across unimaginable distances. To gaze upward was to engage in a dialogue with ghosts, to stand at the edge of the present while surrounded entirely by the past. This recognition shifted more than science, it altered the human imagination. Poets, philosophers, and artists absorbed the revelation that the night sky was an archive. Walt Whitman had once called the stars the eternal watchers, but in the age of relativity, they became witnesses from another time, emissaries of eras humanity could never inhabit. The present moment, once thought absolute, became fragile, dissolved in the endless corridors of spacelum, and still resistance lingered. Many physicists struggled with the concept of a universe where time itself was flexible. Even Einstein himself wrestled with the implications of his equations, particularly when they suggested that time and space could be so distorted as to fold back upon themselves. To some, relativity felt like a betrayal of common sense. The human body, after all, did not feel time stretching or slowing as airplanes flew or as planets orbited. Experience stubbornly clung to Newton's steady rhythm, yet reality, measured with precision instruments, refused to conform. The psychological dissonance was profound. Human beings are creatures of the present, anchored in what feels immediate. Relativity demanded that they abandon this intuition, accepting that now was local, not universal. Across the galaxy, there was no shared moment, no cosmic present. A star exploding in a distant spiral could already be gone, while its light still painted the sky as though it lived. A civilization might rise and fall, its entire history unfolding in silence, while its first signal only began its voyage toward Earth. Thus, a quiet humility began to take root. Humanity, for the first time, recognized itself as a species imprisoned within its own slice of time, unable to see the universe as it truly is. The cosmos revealed itself not as a stage of the present, but as an archive of memory, a museum of ancient light. Every observation was an act of resurrection. Every photon a relic delivered by space itself in this new vision. Telescopes became more than instruments of science, they became machines of remembrance. They carried the eyes across epochs, reaching into the fiery birth of galaxies, the slow dance of stars, the first echoes of the cosmos itself. To look into space was to become an archaeologist of time, brushing away the darkness to uncover layers of existence long vanished. And so, as the dust of debate settled, as resistance yielded to evidence, the truth took hold. The universe itself was not a mirror of the present. It was a tapestry woven in time, its threads stretched by light and gravity, its patterns written across billions of years. The present dissolved, leaving in its place a continuum, vast and unbroken, through which every being, every star, and every thought moved in silence. The first reactions to Einstein's revelation were shock, denial, and awe. But beneath them grew a recognition deeper than science alone, that to exist in this universe is to inhabit not a fleeting moment, but a structure of time beyond comprehension. Humanity had discovered that it was already traveling not by ships or machines, but by the very fabric of reality itself. In the first decades of the 20th century, as the weight of Einstein's revolution settled across physics, astronomy itself began to change its instruments of truth. What once had been little more than stargazing with sharpened eyes and polished glass became a search for clocks hidden in the fabric of the cosmos. Time itself was becoming measurable in the stars. Henrietta Leavitt, working quietly at the Harvard College Observatory, studied faint specks of light on photographic plates. In the subtle flickering of Cepheid variable stars, she uncovered a code. Their brightness waxed and waned in precise rhythm, a pulsation that revealed both their true luminosity and their distance. Leavitt's discovery transformed these stars into cosmic timekeepers, celestial beacons, whose pulses acted as rulers across the darkness. From that point forward, the universe was no longer an unknowable abyss of scattered lights. It was a map etched in cycles, a structure that could be measured, scaled, and placed into the unfolding chronology of cosmic time. If Leavitt gave astronomy its first clocks, Arthur Eddington offered its first proof of Einstein's vision. In 1919, he led an expedition to observe a total solar eclipse on the island of Principe. As the moon darkened, the sun's stars near its edge came into view. Their light bent not because of some flaw in the eye or glass, but because space-time itself curved around the sun's mass. For the first time, humanity witnessed the bending of time's stage. The eclipse became a hinge in history, a moment when Newton's eternal stage dissolved and Einstein's flexible fabric revealed itself to the sky. But the universe still held voices hidden beyond the reach of visible light. In the early 1930s, Carl Jansky, an engineer at Bell Telephone Laboratories, built a rotating antenna to study atmospheric static interfering with transatlantic radio calls. Yet within the hum of noise, he detected something unexpected, a persistent hiss that moved with the stars. Jansky had stumbled upon the first whispers of radio waves from the Milky Way itself. Unwittingly, he had opened a new sense for humanity, one that did not rely on the eye, following in his footsteps. A young amateur astronomer named Grote Reber built a massive parabolic dish in his backyard, a strange metallic flower rising among suburban rooftops. With it, he mapped the invisible sky, revealing that the universe was not silent, but filled with a constant chorus of radio emissions. In those hidden frequencies, the cosmos spoke of violent births of stars, of the swirling hearts of galaxies, of remnants of cataclysmic explosions. Reber had tuned into a deeper layer of time signals that had traveled across eons, bearing witness to events no human had ever seen. And then, in 1965, came a discovery that rewrote the story of beginnings. Arno Penzias and Robert Wilson, working with a horn-shaped antenna in New Jersey, detected a faint, persistent noise, a background hiss that resisted all attempts at explanation. They cleaned the equipment, drove pigeons from the dish, recalibrated again and again, but the signal remained. What they had found was no flaw. It was the oldest light in the universe, the cosmic microwave background. a fossil of the infant cosmos, released when the universe was only 380,000 years old. It still bathed all of space in a faint glow of microwaves. The discovery confirmed the Big Bang, revealing the cosmos itself as a time machine preserving the memory of its own birth, from the pulsing of Kyphids to the bending of starlight, from radio whispers to the ancient microwave echo. Each revelation deepened the same truth. Space was not empty, not silent, not timeless. It was layered, stratified, filled with the remnants of every age. Light, radio waves, microwaves were fossils, records etched into the expanding void. To study the universe was to study the archaeology of time itself, brushing away the silence to uncover traces of what had once been. Every discovery added another layer of wonder and unease. The universe did not merely host time, it carried its fossils, preserved its memories, and whispered them across eternity. And with each new instrument, humanity found itself listening more closely, hearing the voices of a cosmos that had been speaking since the beginning. The story of early investigations did not end with the first sparks of discovery. It deepened, layer by layer, as scientists began to realize that every tool they built was in essence an ear pressed closer to the heartbeat of the universe. The night sky was no longer a silent painting, but a layered archive of histories, each wavelength a record, each signal a trace of something long vanished, yet still present in its echo dot, as Henrietta Leavitt's Kyphids illuminated distances. They also changed the scale of human imagination. For centuries, the stars had seemed fixed, remote, unmeasurable. Now, with their steady rhythms, they revealed that galaxies lay not as smudges upon glass, but as vast island universes, each one millions of light years away. Time itself could be gauged by these flickers, the regularity of their pulse echoing across space like a metronome from another age. When Hubble applied Leavitt's discovery, the universe expanded before humanity's eyes, and with it expanded the scope of cosmic time. The echo of Eddington's eclipse reverberated far beyond its immediate proof. The bending of starlight was not just a vindication of Einstein's equations, but a realization that observation itself had changed. No longer could scientists assume that the path of light was a straight line across an absolute backdrop. Every telescope from that day onward was forced to reckon with the fact that it gazed through a living medium, a fabric warped, stretched, and curved by the masses it contained. To look at the universe was to peer through the very distortion of time itself. Meanwhile, radio astronomy unfolded into an entirely new epoch. Jansky's accidental hiss became, in the hands of Reber and those who followed him, a symphony of cosmic events. The radio sky revealed phenomena invisible to optical instruments, jets streaming from galaxies, pulsars ticking like celestial clocks, the remnants of supernova spreading ghostly shells of energy. With every new frequency, another layer of the universe was unveiled, as though existence itself were a great palimpsest, written over and over, yet still preserving every earlier inscription beneath. These discoveries converged in the mid-20th century upon a single revelation that would shake cosmology at its foundations. The cosmic microwave background, faint but omnipresent, became the first tangible relic of the universe's beginning. It was not a relic of stars or galaxies, but of a time before such things existed. Its photons had traveled unbroken across nearly 14 billion years, bearing the fingerprints of an infant cosmos, dense, hot, and filled with plasma that eventually cooled enough to let light escape. To detect this light was to look directly into the earliest memory of space itself. Astronomers began to realize that the universe was not merely vast in space, but staggeringly deep in time. Each observation pointed not only outward, but backward, into ages when stars had not yet formed, when galaxies had not yet spun themselves into spirals, when the first hydrogen atoms were just beginning to coalesce. The night sky became less a dome and more a tunnel, a passageway into an unfolding chronology where the present dissolved into echoes of countless pasts. Even the instruments themselves became philosophical mirrors. The telescope was no longer simply glass, no longer merely a machine of magnification. It was a time machine, each refinement allowing vision to penetrate further, peeling away cosmic centuries like layers of sediment in an archaeological dig. Every advance in technology, every dish, mirror, detector was an excavation tool. Each photon caught was a fossil from an age long gone, yet carried across the abyss to be deciphered. What made these discoveries profound was not only their technical mastery, but their existential resonance. Humanity was forced to confront the truth that it never sees the universe as it is, only as it was. The stars are not light shining in a shared present. They are archives, some living, some already long extinguished, their final signals still rushing toward us. The very notion of now was stripped from the heavens. To gaze upward was to enter into a dialogue with ghosts of unimaginable antiquity. The impact of the cosmic microwave background was especially disquieting in its philosophical implications. Here was not just an observation of distant stars, but the preserved murmur of the beginning itself. It was as though the universe had left behind a cradle song, endlessly replaying a background hum that could never be silenced. With its detection, the idea of an eternal, static cosmos crumbled entirely. Time had a birth. Space had a beginning. The cosmos, like all things, was a story with an origin, and perhaps an end. Yet with every breakthrough, mystery only deepened. Gifford stars marked distances, but also raised questions about the ultimate scale of the universe. The bending of starlight confirmed relativity, yet left physicists struggling with what it meant to live in a world where geometry itself was mutable. Radio astronomy opened the skies, but also revealed structures and energies far more violent than anyone had imagined. The microwave background sang of origins, yet encoded in its delicate fluctuations were hints of forces still unexplained: dark matter, dark energy, the seeds of cosmic structure itself. By the mid-20th century, the narrative was clear. The universe was no longer an expanse of stillness, no longer a placid stage upon which celestial bodies drifted like ornaments. It was alive with time, heavy with memory, scarred by cataclysms, and filled with light that had traveled across eternity. The sky was not a mirror. It was a record, in the quiet of observatories, in the static of antennas, in the long exposures of photographic plates. Humanity was beginning to hear the voice of time itself. Every discovery seemed to whisper the same truth. The cosmos is ancient, layered, and relentless in its unfolding. To investigate it was to trace not only where things are, but when they were, to enter into the archaeology of existence. And so, the early investigations became more than isolated scientific triumphs. They were the first footsteps into a vast temporal landscape, the dawning awareness that space was inseparable from time, that every star and every wavelength was both a distance and a memory. Each observation was a reminder that the present is fleeting, that the night sky itself is a cathedral of echoes, and that to know the universe is to know that nothing we see is truly now. It began with a single act of patience. In 1995, the Hubble Space Telescope was commanded to fix its gaze on a patch of sky that appeared utterly empty, a small square no larger than a grain of sand held at arm's length. For 10 days it gathered light, pixel by pixel, photon by photon, from the darkness. What emerged from that emptiness was not a void at all, but a cityscape of the cosmos, thousands of galaxies, each one containing billions of stars, their light having traveled for billions of years before reaching the mirror of Hubble. That single image, the Hubble Deep Field, collapsed time into a single frame. It revealed not just distant galaxies, but ancient ones, preserved as they were when the universe itself was still in its youth. A glance upward was no longer a glance into the present. It was a plunge into cosmic prehistory. The revelation of the deep field changed astronomy forever. It was not only an image, it was a temporal archive. Every dot of light became an epoch, every smudge of starlight a frozen chapter in the evolution of galaxies. The act of looking became an act of remembering, of witnessing what no human eye was ever meant to see, the birth pangs of cosmic structure, still unfolding across a gulf of time so great it seemed to defy comprehension. Yet even as light carried these ancient records, the universe provided other instruments of memory. Gravity itself, predicted by Einstein, became a lens, bending light into arcs and rings around massive clusters of galaxies. These gravitational lenses acted as natural telescopes, cosmic mirrors amplifying whispers from the deep past. Behind the curved reflections lay galaxies otherwise invisible, faint, ancient structures magnified across space and time. What seemed at first like distortions were in truth revelations. Light stretched and rerouted across billions of years to reach us. In the bending of starlight, the cosmos itself performed the task of preservation, ensuring that even the faintest echoes could still be heard. Supernova added yet another layer to the architecture of cosmic memory. When stars reached their violent ends, their explosions became both beacons and clocks. Their brilliance, momentary but predictable, allowed astronomers to gauge distances with unprecedented precision. Type Ia supernova, bright enough to be seen across galaxies, revealed not only where these stars had been, but how quickly the fabric of space itself was stretching between them. In their fiery deaths, they traced the heartbeat of the universe, marking its expansion and whispering of a strange force, dark energy, that seemed to be accelerating the flow of time itself beyond light. Stranger messengers traveled through the void. Neutrinos, particles born in the hearts of dying stars, carried with them secrets from places photons could not escape. They were ghost-like, slipping through matter with barely a trace, crossing the gulfs of space almost untouched by the ages. When they arrived on Earth, detected in underground caverns and icy observatories, there were signals from the cores of collapsing suns, messages that had traveled across time to deliver the story of stellar death. Unlike light, they carried no distortions, no delays from scattering or absorption. They were the unbroken voices of cataclysm, whispering from the past. Then, in 2015, humanity heard the universe in an entirely new way. LIGO, the Laser Interferometer Gravitational Wave Observatory, recorded the trembling of space-time itself. Ripples had crossed the cosmos for over 1 billion years, born in the collision of two black holes spiraling into one another. They arrived not as light, not as particles, but as vibrations in the fabric of reality, space-time ringing like a drum struck by the hand of creation. For the first time, the cosmos revealed its history not through images or signals, but through the direct shiver of its own structure. Each wave was a memory, not of light that had traveled across time, but of time itself, carried forward in the oscillations of the universe's geometry. Together, these breakthroughs transformed the very idea of observation. The telescope, the detector, the observatory, none were simple windows. Each was a machine tuned to a different kind of messenger: photons, neutrinos, gravitational waves. Each messenger carried with it a different past, a different layer of the cosmic story. To see, to hear, to feel the universe was to experience time through many senses at once. What emerged was not just a deeper understanding of the cosmos, but a deeper sense of awe. Space was not an expanse to be crossed, but a medium filled with signals from every age. Every new instrument added another strand to the weave, another voice to the chorus of time. The night sky was not silent. It was a cathedral of echoes. Every galaxy, every explosion, every ripple in space-time was a memory, preserved and carried forward, waiting to be deciphered. And in these observations, one truth grew unmistakable: space itself is the archive of time. The further humanity reaches into its depths, the further it steps into its own origin. Each discovery is a reminder that to look outward is to travel backward, that the universe itself is the most intricate time-travel machine, one that requires no invention, only the patience to listen. The revelations of the Hubble Deep Field did not end with a single image. Years later, astronomers pushed further still, extending the exposure times, narrowing their gaze, and creating the ultra-deep field, a vision even deeper into antiquity. What it revealed was staggering. Galaxies not yet mature, their shapes irregular and primitive, flickering faintly as the first great structures of the cosmos took form. These galaxies were fossils of a universe still in its adolescence, fragile and chaotic, yet destined to become the spirals and ellipticals that now dominate the night sky. The deeper the telescope looked, the younger the universe appeared. Each new observation unearthing layers of time like an archaeologist brushing away soil to reveal bones older than memory itself. Yet the sky does not give up its secrets in one voice alone. Where Hubble's eyes pierced the darkness, other instruments expanded the reach of perception. The Chandra X-ray Observatory unveiled a universe blazing in wavelengths invisible to human sight, where black holes fed and quasars outshone entire galaxies. To see in X-rays was to glimpse violence on scales too vast for imagination. Energy erupting from the cores of galaxies when the cosmos was still in its earliest stages. These high-energy signals, traveling for billions of years, carried stories of matter torn apart and flung into space. Reminders that the early universe was both a cradle and a battlefield. Gravitational lensing, too, became more than a curiosity. It became a tool of precision. Astronomers learned to read the distortions, to measure the invisible scaffolding of dark matter that shaped the cosmos. By studying how light bent, they traced the unseen skeleton of the universe, an architecture not of stars but of mass itself. Each arc of bent starlight was a relic of both distance and time, revealing galaxies so faint and so ancient that without gravity's magnification they would remain forever hidden. It was as though the universe, aware of the limitations of human technology, had left behind its own instruments of magnification, cosmic mirrors that allowed the story of time to be glimpsed. Supernova, once seen as singular cataclysms, became an essential chronometer, when two teams of astronomers in the late 1990s studied the light curves of distant Type Ia explosions. They expected to confirm the slowing of cosmic expansion. Instead, they found the opposite. The universe was not decelerating under the weight of gravity, but accelerating, driven by some mysterious, unseen pressure that came to be called dark energy. The revelation shook cosmology to its core. These dying stars, scattered across galaxies billions of years old, had become cosmic witnesses to a deeper truth, that time itself was stretching ever faster, that the universe was not simply a memory but an evolving machine, propelling itself forward with increasing speed. In their fleeting brilliance, these explosions had traced not just the size of the cosmos, but the destiny of time itself. Meanwhile, beneath the surface of Earth, detectors waited in silence for the messengers stranger still. Neutrinos so elusive that trillions pass through every human body each second unnoticed, occasionally betrayed their presence. In 1987, a handful were caught arriving from supernova 1987A, the death of a star in the Large Magellanic Cloud. These ghostly particles had crossed the void almost unscathed, carrying with them a signal from the star's very core, a whisper of nuclear collapse that no telescope could ever see. Decades later, the Ice Cube Observatory, buried deep in Antarctic ice, expanded this pursuit, listening for neutrinos from the farthest reaches of the cosmos. Each detection became a letter carried across eons, an incorruptible record of stellar violence, preserved in particles that had journeyed through galaxies, through clusters, through billions of years of expanding space, and then, the most haunting voice of all, the trembling of space-time itself. When LIGO confirmed the first detection of gravitational waves in 2015, the universe became audible. The collision of two black holes had sent ripples cascading through the fabric of reality, distortions that had traveled for more than 1 billion years before brushing past Earth. These were not mere signals of light, not ghostly particles slipping by, but the vibration of time itself, as though the cosmos were ringing like a great instrument. In their rising and falling frequencies, scientists heard the memory of a cataclysm that occurred long before humanity even existed. The present moment had become a stage upon which ancient collisions continued to play. This was not the end, but the beginning of a new era of multi-messenger astronomy. Light, neutrinos, and gravitational waves, 3 distinct languages, were now woven together to tell the story of time. In 2017, the collision of 2 neutron stars was observed across all 3 messengers simultaneously. Telescopes recorded the light of the explosion. Detectors caught the ripple of space-time, and neutrino observatories listened for the whisper of particles. Together, they revealed the creation of heavy elements, gold and platinum forged in the fires of merging stars. A cosmic alchemy carried across billions of years to be discovered by human instruments. This was time travel made manifest, ancient events inscribed in multiple voices, decoded in the present. With each discovery, the definition of a telescope expanded. No longer simply a lens gathering light, it became a device for tuning into the chorus of the universe, each tuned to a different messenger of memory. Optical telescopes captured photons, radio dishes caught cosmic whispers, neutrino detectors read ghostly signatures, and gravitational observatories recorded the trembling of the void. Together, they revealed that space itself is layered with memory, that every particle, every wave, every ripple is a chronicle of the past. What emerges from these breakthroughs is a portrait of space, not as emptiness, but as archive, a grand record where nothing is truly lost. only carried forward in another form. The light of galaxies, the distortions of lenses, the deaths of stars, the whispers of neutrinos, the vibrations of space-time, all are testimonies, preserved in the medium of the universe itself. And so, the question grows louder, more insistent. If every act of observation is an act of time travel, if every signal is a fragment of history, then perhaps the universe itself is not only a place in which time unfolds, but the very machinery by which time is preserved, stretched, and delivered. Every observation is a journey backward. Every detection is a communion with what has long since passed. Space is not just the backdrop of existence, it is the ultimate time travel machine. The deeper humanity gazes into the universe, the more it seems to enter a paradox. The galaxies at the farthest edges of perception do not appear as they are, but as they once were, their light slowed, stretched, and softened by the expansion of space. They are frozen in ancient poses, like actors paused mid-motion in a cosmic play whose lines are still being spoken billions of years later. To look across the vastness is to watch time itself hesitate, to see epochs that ended before Earth had even formed, still alive in their luminous echoes. The more distant the gaze, the further back the journey. Each photon is not simply light, but a courier from the past, bearing witness to events long extinguished, preserved by the architecture of the universe itself. This strangeness is not confined to the distant edges of space. Time itself bends and buckles around the most massive objects in the cosmos. Near a black hole, the ordinary rhythm of seconds and minutes begins to fracture. Photons, straining to escape the gravity of such a collapse, are stretched into longer and longer wavelengths, reddened into near invisibility. To an outside observer, a clock falling toward the abyss seems to tick slower and slower, its hands freezing at the brink of the event horizon. In that final suspended instant, the very notion of time dissolves into paradox. For the falling traveler, moments pass normally. For the distant witness, the descent never completes. Black holes do not simply devour matter, they ensnare time itself, creating regions where the past and future seem trapped, where events appear eternal yet unreachable. Einstein's equations had already hinted at this unsettling truth. Time is not universal. Motion itself alters its flow. The so-called twin paradox makes this tangible. One twin embarks on a journey at near light speed, while the other remains on Earth. When they reunite, the traveler has aged less than the one who stayed behind. This is not an illusion, not a trick of perception, but the reality of space-time. To move through space is to alter one's trajectory through time. Every spaceship that accelerates, every particle that nears the speed of light, becomes a tiny demonstration of time travel into the future. The cosmos itself performs this act on the grandest scale imaginable. As space expands, it stretches the passage of time embedded within it. Ancient light is not only delayed in its arrival, it is elongated, slowed, turned into a record of a younger universe refracted through the fabric of growth itself. A galaxy whose light has traveled for 10 billion years is not simply far away in space. It is 10 billion years younger than our present. Its image sculpted by the stretching of reality that has occurred in the interim. The expansion of the universe is not just a swelling of distances, but the slow unfolding of time's grand narrative. Written in starlight, at the edges of knowledge lies the most haunting mystery of all, the event horizon paradox. According to relativity, any information falling into a black hole appears to freeze at the threshold. smeared across the surface as though etched into a cosmic archive. Yet quantum theory insists that information cannot be destroyed. If both are true, then black holes are not only traps of gravity, but strange vaults of memory, preserving every detail of everything that has ever fallen within them. To observe such a horizon is to witness a place where time itself appears immobilized, where the past is forever painted on the edge of the abyss. Whether that information is ever released, perhaps in subtle radiation, perhaps in ways still unknown, remains one of the deepest puzzles of modern science. These realizations converge into a single revelation. Time travel is not an exotic fantasy reserved for science fiction. It is the ordinary condition of the universe. Every act of observation is an act of looking backward. Every distant star is a preserved page of history, every galaxy a portrait of an earlier age. To gaze into the sky is to traverse millennia in an instant, to touch moments that long precede our own. The night is not a mirror reflecting the present, but a cathedral of memory, where the light of the past continues its patient pilgrimage toward us in this way. The mystery deepens not because the universe grows stranger with each discovery, but because each discovery reveals how much more entangled time and space truly are. The cosmos does not simply contain history, it is history. The passage of time is not something separate from the stars, the galaxies, the black holes. It is the thread binding them, stretching them, shaping them. Every photon, every ripple, every orbit is part of the grand chronicle, a testimony that the universe itself is the keeper of time. And so, in the silence of the night, beneath a dome of ancient light, humanity is confronted with a truth at once humbling and profound. The act of looking outward is inseparable from the act of traveling backward. The universe, vast and patient, carries its own memory across every horizon, offering glimpses of ages long past to those willing to wait, to listen. To see, the fabric of time reveals itself most clearly, not in cosmic extremes alone, but in the subtleties of the everyday. Even the technology orbiting above Earth bears silent witness to time's fluidity. The network of satellites that guides navigation relies on clocks so precise they can measure the drift of nanoseconds. Yet if these satellites were to trust only their onboard time, the system would collapse, moving rapidly in orbit while also sitting above much of Earth's gravitational pull. Their clocks tick at a rhythm different from those on the ground. General relativity predicts this dual shift. Gravity slows time, velocity slows time, and in orbit these effects compete. Without constant corrections derived from Einstein's equations, a navigator on Earth would soon find themselves miles astray. In this way, the strange elasticity of time is not confined to black holes or distant galaxies. It is etched into the devices that guide ships, planes, and phones across the surface of our planet. But if such variations unfold within the gentle well of Earth's gravity, what then in the crushing grip of neutron stars or the supermassive black holes at galactic centers? Their time dilates to extremes, stretched like liquid glass across the event horizon. Around Sagittarius A*, the black hole at the heart of the Milky Way, matter circles at nearly the speed of light, glowing as it plunges toward oblivion. To an observer nearby, seconds would thicken into hours, hours into years. A person watching from a safe distance would see that infalling material never quite completes its journey, as though trapped in perpetual approach. Yet for the matter itself, the plunge is inexorable, crossing the horizon in finite time, vanishing into mystery. Such paradoxes reveal that there is no single, universal rhythm binding all observers together, each path through. Space-time carves its own measure of duration. Cosmologists, searching beyond individual objects, discover that the universe itself has written time into the light of galaxies. As space expands, it stretches not only distances but the waves of light themselves. What begins as blue or white emerges after billions of years of travel as red, faint, and drawn thin. This cosmological redshift is more than a Doppler effect. It is a clock carved into the cosmos. By measuring the degree of stretch, astronomers reconstruct not only distance but age, translating faint glimmers into time stumps on the grand ledger of the universe. When astronomers say a galaxy lies 13 billion light-years away, they are not merely measuring geography. They are announcing that the image before their eyes is a relic of a universe that was only a few 100 million years old. This deep look backward culminates in the faintest, oldest light of all, the cosmic microwave background. Discovered in 1965 by Arno Penzias and Robert Wilson. It is the afterglow of the Big Bang itself, cooled and stretched by nearly 14 billion years of expansion. To study its subtle patterns is to read the very first pages of time, when the universe was less than 400,000 years old. The ripples embedded in this ancient radiation reveal where matter began to cluster, where stars would one day ignite, where galaxies would emerge. It is not simply light, but memory, a fossil etched into the fabric of reality, carrying the infancy of time forward into the present. Yet these fossils remind humanity that the arrow of time is not fully understood. Entropy, the principle that disorder tends to increase, has long been thought to dictate its flow. The universe evolves from order into chaos, from smooth simplicity into intricate complexity, from low entropy into high. But why this should be so remains unsolved. If the laws of physics appear time-symmetric, why then does the universe insist on marching forward, never backward? The expansion of the cosmos seems to act as both stage and script, pulling time along with its growth. As galaxies drift apart, as radiation cools, as stars burn out, the flow of time is inscribed into the very direction of the universe itself. At the boundary where relativity and quantum mechanics collide, further mysteries bloom. The holographic principle, suggested by Gerard T. Hooft and Leonard Susskind, proposes that the information within a volume of space may be fully described on its boundary, as if reality itself were projected from a two-dimensional surface. If true, time as experience within the universe may be an emergent phenomenon, a shadow cast by deeper laws inscribed not within space-time, but upon its edges. In this view, the event horizon of a black hole does not merely freeze time for distant observers. It encodes the history of everything that has crossed it, preserving a ledger on its surface. The paradox of information may not be a failure of physics, but a clue that time itself is less fundamental than once believed. Such theories remain speculative, but they touch upon a truth already evident in every telescope, every detector, every equation. The experience of time is inseparable from perspective. A star collapsing into a supernova may send both light and neutrinos racing across space. The light, slowed by interactions, may arrive hours later than the ghostly neutrinos, even though both were born in the same instant. A gravitational wave, rippling through space-time, may reach detectors at LIGO before the visible explosion is ever seen. Each messenger carries its own version of the story, each one a different translation of the same event. Together, They reveal that time does not flow as a single river, but as a braided delta, splitting, converging, and rejoining, depending on how one chooses to listen. And so the mystery deepens. To look into the night sky is not to see a simple present, but a layered archive. Some light is billions of years old, stretched thin across time's canvas. Some particles arrive nearly instantaneously, silent couriers of stellar death. Some waves of space-time vibrate with the echoes of ancient cataclysms, traveling unscattered across the ages. Each is a witness, each a page in the chronicle of the cosmos. Humanity lives suspended in this weave, bound by seconds that pass relentlessly on Earth, yet surrounded by a universe where seconds lose their certainty. In this grand cathedral, time is not fixed, not singular, not absolute. It bends, slows, quickens, and stretches, shaping reality into a tapestry both strange and beautiful. Every observation becomes an act of travel, every calculation a brushstroke on the mural of ages. The realization is as humbling as it is profound. Time travel is not invention, not speculation, not dream. It is the ordinary condition of existence in a universe vast enough to preserve its past in the light that still journeys toward us. To look outward is always to look backward. To measure, to observe, to reflect is to become a participant in the cosmic memory. The present is never alone. It is always accompanied by the shadows of what has been, carried across the silence of space, and somewhere, beyond the limits of vision, beyond the reach of instruments, the future already waits, shaped invisibly by the fabric of space-time. The universe, ever expanding, ever unfolding, carries all of time within it, the past still arriving, the present already fading, the future being drawn toward us on currents unseen in the grand story of time. There comes a point where the known dissolves into speculation, where the firm scaffolding of observation gives way to the faint outlines of possibility. At this extreme edge of science, the universe whispers of structures so strange that they seem to belong more to dream than to physics. Yet they rise not from fantasy, but from equations themselves, the raw mathematics of space-time, carrying hints of paths not yet walked. Among these imagined pathways stand first conceived as Einstein-Rosen bridges in 1935, in the language of general relativity. A black hole in its mathematical mirror could, under the right conditions, form a tunnel linking distant regions of space-time. The geometry suggests shortcuts, corridors through the cosmic fabric, where a traveler might leap across galaxies, or perhaps even across eras. But equations are indifferent to human desires. These bridges collapse almost as quickly as they appear, pinching shut before anything can cross. For decades, theorists have sought conditions that might hold them open, exotic matter with negative energy density, as permitted by quantum fluctuations, seems one key. Such matter has never been harnessed, yet its faint traces appear in the Casimir effect, where empty space itself pushes objects together. Here lies a tantalizing possibility that the vacuum may hold the resources to bend not only distance but chronology. Even without tunnels, relativity admits stranger geometries still. Kurt Gödel, the mathematician famed for his incompleteness theorems, discovered in 1949 a solution to Einstein's equations where the universe itself rotates. In this rotating cosmos, time becomes a circle, and closed time-like curves emerge naturally. Within such a model, one could, in principle, return to one's own past simply by moving along space-time's curve. The solution was unsettling not because it broke mathematics, but because it was fully consistent with it. Einstein himself, though intrigued, was disturbed. For if the laws of physics allow such loops, then the linear flow of time is not inevitable, it is contingent, a feature of our particular cosmos, not a rule written in stone. Black holes, too, have long been teased with the possibility of gateways. At their core lies the singularity, a point where density and curvature soar toward infinity. Some models suggest that a singularity might connect not to an end, but to another region of space-time, a white hole from which matter only emerges. Such structures, if stable, could serve as portals, though none have been observed, and many physicists doubt they could exist within our universe. Yet the mathematics leaves open the possibility that black holes are not only graveyards of stars, but junctions in the hidden architecture of the cosmos. Other theories push the imagination further still. Cosmic strings, hypothetical defects in space-time left over from the early universe, may stretch across vast distances. Infinitely thin, yet enormously dense, they would warp space-time around them like a blade slicing fabric. If two strings were to pass, their interaction could, in theory, permit travel backward in time. No evidence for such structures has been found, though gravitational wave observatories now listening to the sky may one day detect their tremors. If they exist, they would be relics of creation itself, scars left behind by the universe as it cooled from its fiery birth. Yet with every door that mathematics opens, paradox follows. If time loops are possible, could one prevent one's own existence? Could messages sent backward erase their own origin? These paradoxes, known as violations of chronology, challenge the coherence of reality itself. Some physicists argue that the universe enforces a chronology protection conjecture, as Stephen Hawking once proposed, ensuring that the fabric of time forbids such contradictions. Others suggest that quantum mechanics may blur the paradox, replacing clear causality with a probabilistic haze where all outcomes coexist until measured. In either case, the message is humbling. The mathematics permits, structures reality may not. And until observation speaks, they remain possibilities suspended on the frontier of thought. This extreme edge of science is a landscape both intoxicating and perilous. Wormholes, G-Gel universes, singularities, cosmic strings, each is born from rigorous equations, each a mathematical truth. But whether nature has chosen to weave them into the fabric of the actual cosmos remains unknown. The universe, vast and silent, does not yet reveal such secrets. Still, their presence within the equations carries meaning. They remind humanity that the familiar flow of seconds and years is not the only way time might unfold. They suggest that the laws of physics are not chains, but canvases, broad enough to paint realities unlike our own. They open the mind to the possibility that beyond the horizon of the observable, or within the hidden layers of quantum structure, time may twist, bend, and fold in ways unimaginable. For now, they remain whispers, tantalizing structures drawn not in starlight but in ink, glimpsed not through telescopes but through mathematics. Yet in these whispers lies both a challenge and an invitation to push the boundaries of knowledge, to question the inevitability of time's arrow, and to wonder whether reality is stranger still than imagination allows. At the boundary where speculation meets the possible, physics enters a realm of thought experiments as vivid as myths, and yet bound to equations as precise as music. Wormholes, cosmic strings, rotating universes, each hints at a cosmos where the arrow of time is not fixed, but malleable. Yet the conversation does not end there. At this frontier, even the most fundamental concepts, cause, effect, memory, and destiny, begin to blur. The paradoxes that arise are not trivial curiosities. They strike at the core of what it means for events to unfold. The so-called grandfather paradox, where a traveler interferes with the conditions of their own birth, is a thought experiment as old as time travel's imagination. In physics, such contradictions are formalized as causality violations. If mathematics admits closed loops in spacetime, the logical structure of reality itself is threatened. Some theorists propose a subtle escape, self-consistency conditions, where any event that occurs within a loop must align with history as it already exists. In this view, free will is constrained. One may travel into the past, but only along paths that fulfill the story already written. Time, then, becomes not a canvas of possibilities, but a tapestry in which every thread is already woven. Quantum physics offers another lens. At the smallest scales, particles do not behave like deterministic actors, but like shimmering probabilities. In this framework, paradoxes might dissolve into multitudes. If one action in the past would erase the conditions for a traveler's existence, then the universe may branch, splitting reality into parallel outcomes where both possibilities coexist. Such interpretations, like the many worlds view, extend the paradox into a multiverse of diverging histories. If true, time travel would not rewrite the past, but rather carve new rivers alongside the old, leaving the original flow intact. The paradox is sidestepped, but at the price of multiplying realities beyond counting. Hints of time's strange pliability emerge even within quantum theory itself. Some interpretations of entanglement suggest correlations that extend not only across space, but across time. Experiments in quantum delayed choice have shown that decisions made in the present can influence the behavior of particles seemingly already measured. Though no causality is broken, information is never sent backward. These results suggest that the universe is not bound by the classical intuition of sequential events. Instead, past and future appear braided together in ways that defy ordinary chronology. To some, these experiments whisper of a deeper symmetry. Perhaps the laws of physics do not truly distinguish past from future, but only appear when scaled to human experience. If wormholes and rotating universes are the speculative monuments of relativity, then quantum loops and entangled histories are the shadows cast by the microscopic. Together, they suggest that time's arrow, so firm in daily life, may not be absolute. The cosmos could harbor layers of temporal structure invisible to ordinary perception. Structures where the flow of seconds is not inevitable, but emergent. The possibility of time machines arises again in string theory, the ambitious framework that seeks to unify gravity with quantum physics. Within this model, space-time is not smooth but woven from vibrating strings, curled into dimensions beyond the familiar four. Certain solutions to string equations permit closed time-like curves, paths through the higher dimensional geometry where a traveler could return to their own origin. Yet as always, such paths encounter the guardians of paradox. Mathematics allows them, but questions of stability, energy, and consistency remain unresolved. Whether the universe tolerates such loops, or whether some deeper law forbids them, remains one of the great uncertainties. Even outside advanced mathematics, the cosmos itself presents riddles that echo these possibilities. Black holes, for instance, embody both the promise and peril of time manipulation. Near the event horizon, time dilates endlessly, freezing events as if painted on the surface of eternity. To a distant observer, information falling into a black hole appears suspended forever at the edge. This has led some to imagine the horizon itself as a kind of temporal recording device, a cosmic ledger that preserves history indefinitely. Yet the mystery deepens with Hawking radiation, which slowly evaporates black holes. If the horizon is both frozen and impermanent, where does information ultimately go? The information paradox remains unresolved, hinting that the relationship between time, gravity, and quantum mechanics is far richer than yet understood. Cosmic expansion itself offers another strange mirror. If the universe's acceleration continues, driven by dark energy, distant galaxies will eventually slip beyond our observable horizon. Their light, stretched endlessly by expansion, will never arrive. To us, they will fade into silence, as though erased from existence. Yet in another frame, they still burn, still evolve, still play their part in the cosmic story. Here time is fractured by perspective. One observer sees eternal absence, another sees persistence. If wormholes or strings tempt with shortcuts through space-time, the expanding cosmos itself demonstrates that chronology is never universal, that what is, forever gone for one, is still present for another. At the edge of theory, the tantalizing theme repeats. Mathematics opens doors that nature may not. Wormholes demand exotic matter. Gidgel's universes demand a rotation the cosmos does not appear to possess. Cosmic strings require relics of symmetry-breaking events we have yet to detect. Quantum entanglement teases with non-locality, but stops short of causal violation. Again and again, nature reveals its caution. It permits hints, glimpses, structures that nearly reach across eras, but withholds the final step. It is as if the universe is built to inspire the thought of time travel, but denies its realization in practice. And yet, perhaps that denial is not permanent. Just as radio waves, once unimagined, became the medium of communication across the globe, so too might the hidden symmetries of time one day be unlocked. For now, the edge remains. A frontier of wormholes that collapse, strings not yet found, paradoxes unresolved. It is a landscape where speculation is not idle fantasy, but a compass pointing toward what physics still must explain. Here, at this boundary, science meets philosophy. Time is revealed not as a singular thread, but as a labyrinth, its corridors hinted at in equations, its doors closed for now. The question lingers. Is the universe protecting its secrets, or merely waiting for understanding to catch up? At this edge, humility becomes inevitable. Humanity peers into equations that permit impossible geometries and asks, are these glimpses of reality or mirrors of imagination? What is certain is this. At the extreme edge of science, time is not the simple march once assumed. It is pliable, paradoxical, capable of folding into itself. And in that pliability lies the possibility that the cosmos itself is not only a witness to history but its architect, shaping what may and may not be remembered, what may and may not return. Time, as lived by humanity, feels like a current, ever flowing forward, carrying memory into oblivion and leaving possibility still unborn. Yet physics reveals that this river is not uniform. It bends, slows, accelerates. It does not wash over all observers equally. In the mainstream corridors of science, time travel is not relegated to fantasy. It is already proven in the smallest, most precise measurements. and it is written in the equations that govern both the cosmos and the body of an astronaut in motion. The most unambiguous doorway into the future arises from Einstein's relativity itself. When objects move at speeds approaching that of light, their clocks, their metabolism, even the rhythm of their very atoms, begin to tick more slowly than those of their stationary counterparts. The mathematics is exact, the effect measurable. In laboratories, particles born in accelerators live far longer than nature would otherwise allow. Their internal clocks stretched by velocity. The twin paradox illustrates it in human terms. One twin journeys at near light speed across the stars, while the other remains on Earth. Upon reunion, one will have aged decades, the other mere years. Time is no longer a universal measure, but a pliable quantity. Tailored to the path through space-time each traveler takes, even without rockets or cosmic voyages. This truth is confirmed every second above the planet. Global positioning system, satellites, orbiting high above Earth, carry atomic clocks that diverge from those on the ground. They tick faster due to weaker gravity, but slower due to orbital velocity. The two effects nearly balance, yet the difference is measurable. If not corrected, navigators and smartphones would drift miles off course within days. Every successful GPS calculation is an unconscious act of time travel accounting, an acknowledgement that the flow of time depends on perspective, and that without relativity, even the modern world would lose its bearings. Gravity itself sculpts time in ways equally profound. Near massive objects, space-time is compressed and clocks run slower. This gravitational time dilation has been measured on mountaintops, in aircraft, even between the base and summit of skyscrapers. A person standing at sea level ages infinitesimally slower than one on a plateau, simply because the Earth's gravity is stronger nearer the core. In the shadow of extreme objects such as neutron stars or black holes, this effect becomes dramatic. To an outside observer, time for someone approaching the event horizon appears to slow to a crawl, stretched into near immobility. Space itself becomes a natural time machine, where gravity dictates the tempo of existence. These are not speculations. They are daily realities. The future is accessible, not through paradoxical loops or exotic devices, but through the simple fact that motion and mass bend time. To travel forward into tomorrow, faster than those left behind, requires only speed and gravity tools the cosmos already provides. Yet another frontier of mainstream understanding lies in the arrow of time itself. Unlike relativity symmetry, entropy gives time its direction. From the moment of the Big Bang, the universe has been expanding, cooling, and unraveling into ever more disordered states. A glass shatters. It does not reassemble. Heat flows from warm to cold. It does not reverse. Entropy, the measure of disorder, increases inexorably, defining time's one-way journey. In cosmology, this arrow stretches from the primordial simplicity of a newborn universe toward the heat death of a diffuse and exhausted future. Time, in this sense, is nothing more than the unfolding of entropy on a cosmic scale, the gradual smearing of order into chaos. Cosmology also reminds us that time itself is not eternal. In inflationary models, the rapid expansion that birthed the observable universe did not occur within time, but created it. Before inflation, before the Big Bang, the very notion of before may be meaningless. Time, as a dimension, began with the birth of space-time itself. In this view, time is not a river flowing eternally, but a feature that emerged. Like space, out of an initial state of pure potential. This realization reshapes the mystery. Time travel is not merely about moving within time, but confronting the possibility that time itself is contingent, an emergent property of the universe rather than a pre-existing stage. Among physicists, one interpretation extends this further: the block universe. In this vision, past, present, and future all coexist, etched into the four-dimensional continuum of space-time. Time does not flow. It simply is. Every moment, from the birth of the first star to the fall of the last, is equally real, equally permanent, like frames in a film reel. The sensation of passage is an artifact of consciousness moving from one coordinate to another. In this interpretation, time travel is not motion at all, but perspective. To see the past would not mean rewriting it, but perceiving what is already inscribed. Every star's death, every choice, every heartbeat is forever frozen within the structure of spacing. Mainstream science, however, draws a careful boundary. To the future, the door stands open, firmly grounded in relativity, confirmed by experiment. To the past, it remains locked, not because mathematics cannot imagine the key, but because reality seems to deny its use. Backward travel confronts paradox, entropy, and the symmetry breaking that gave birth to time itself. Even in the block universe, the past may be real, but it is not revisitable. Humanity can move forward, faster or slower, but it cannot return. Here lies the paradox of scientific humility. Physics proves that time is not what it seems, yet insists that much of what imagination desires remains forbidden. The universe allows glimpses of a future accessible by speed, gravity, and entropy's unyielding direction. It denies, at least for now, the dream of walking backward across history. Forward travel is not speculation but fact, written into every orbiting satellite and every accelerating particle. Backward travel remains the edge where mathematics tempts and reality resists. And so, within the mainstream, the verdict is clear. The universe is a time machine, but one that carries all its passengers toward the future. The dream of revisiting the past, of unmaking or reliving, belongs to the speculative horizons. Yet even in this limitation lies a profound wonder, the recognition that time itself is not universal, not absolute, but a landscape that bends, stretches, and reshapes itself under the laws of physics. Humanity is not merely drifting through time, it is already navigating its currents, unknowingly traveling into futures different from one another, carried by the strange and beautiful geometry of space-time, beneath the familiar flow of time that governs daily existence. Science has carved out demonstrations so precise, so undeniable, that the pliability of time becomes an experimental reality rather than an abstract thought. The mainstream theories of time travel rest not on myth or imagination, but on clocks, particles, and satellites, instruments of measurement that refuse to lie. And in their ticking and decay, they reveal that time itself is elastic. One of the most striking proofs came in 1971, when physicists Joseph Haffel and Richard Keating boarded commercial airliners with atomic clocks. They flew eastward around the Earth, then westward, and compared their airborne clocks to those that had remained on the ground. The results were subtle but exact. The clocks aboard the planes disagreed with those on Earth by tiny fractions of a microsecond, precisely as predicted by Einstein's relativity. Motion through space had changed the rate of time's flow. It was not a trick of perception or calculation, but a measurable reality. Humanity had, in that experiment, taken the first deliberate steps into the future at different speeds. Particle physics reinforces the lesson. Muons, unstable particles born in the upper atmosphere from cosmic rays, decay in millionths of a second. According to their natural lifetime, few should survive long enough to reach detectors at Earth's surface. Yet many do. Their near-light-speed descent extends their lifespan, allowing them to cross distances that, without relativity, would be impossible. To the muon, its clock ticks normally. To observers on Earth, the muon lives longer, stretched by the dilation of time itself. Each one that arrives at the surface is a messenger, carrying proof that velocity bends existence. Even spacecraft, silent wanderers beyond Earth, confirm this truth. Probes journeying to the outer solar system are tracked with astonishing precision. Their signals timed against atomic standards on Earth, without accounting for relativity. Their trajectories would appear inexplicably wrong. Each course correction, each pulse of radio communication, carries within it the acknowledgement that time is not absolute, but dependent on gravity and motion. The universe, it seems, is filled with natural laboratories of time travel. Stars orbiting close to the supermassive black hole at the heart of the Milky Way move in such extreme gravitational fields that their clocks tick differently from stars farther out. Observations of these orbits, measured by instruments like the gravity interferometer at the Very Large Telescope, confirm Einstein's predictions with extraordinary fidelity. These stars dance not only through space but through stretched and compressed layers of time, and yet, amid these confirmations, a boundary persists. The mainstream consensus holds firm. Forward travel is real, backward travel is still forbidden. The laws of physics resist reversals, not merely because of paradoxes of causality, but because of entropy's relentless march. The universe, as observed, does not unspool in reverse. Radiation disperses, matter decays, galaxies drift apart. In all of physics, no experiment has ever captured entropy flowing backward. No clock spontaneously rewinding. Still, within the mainstream, theories continue to refine the edges of understanding. The inflationary model of cosmology provides a profound backdrop. During the earliest fraction of a second, the universe expanded faster than the speed of light, stretching quantum fluctuations into the seeds of galaxies. This event did not take place in time. It created time. In this sense, every moment since is a continuation of that primordial unfolding. The arrow of time is not an illusion, but a cosmic inheritance. It was imprinted in the very birth of the universe. The block universe interpretation, too, lingers at the threshold of philosophy and physics. In this vision, there is no flow at all. Every moment exists simultaneously, etched into space-time like grooves in crystal. The sensation of moving through time is akin to reading a book one page at a time, while the entire story already exists, bound and complete. To physicists, this interpretation is consistent with relativity, but it unsettles the human mind. If the past and future are as real as the present, then time travel becomes less about traversing a river and more about shifting perspective along a frozen landscape. Yet, even in this static picture, entropy still whispers its dominance. For though the future may be written, it is written in a direction, a gradient from order to disorder, from low entropy to high. The block universe may contain every moment, but the experience of consciousness is shaped by this thermodynamic current, giving the illusion of passage. The mainstream stance, then, is both humbling and exhilarating. On the one hand, it denies the extravagant loops of science fiction, the journeys backward to rewrite history, the encounters with ancestors long gone. On the other, it offers something even stranger, proof that the future is accessible, and that humanity already participates in time travel every day. Each orbiting satellite, each high-speed particle, each star circling a black hole demonstrates that time is malleable. In this light, forward time travel ceases to be exotic. It becomes the ordinary condition of a universe shaped by relativity. The astronaut who ventures near light speed will return younger than those left behind, not by magic, but by geometry. The climber ascending a mountain will gain an infinitesimal fraction of a second over those at sea level. The universe is constantly stretching, bending, and warping time, and humans, whether aware or not, are passengers on that journey. The recognition carries a quiet profundity. It means that the cosmos is not a neutral stage upon which life unfolds, but an active participant, reshaping the tempo of every existence. Time is not a universal drumbeat heard the same by all, but a shifting rhythm, different for each observer, tuned to the path they take through spacetime. And so, within the mainstream vision, the dream of time travel is both fulfilled and denied. Humanity can never turn back the clock, but it can stretch the present into the future, riding the curvature of time itself. The universe does not permit journeys into yesterday, but it ensures that every tomorrow is reached at a pace shaped by speed, gravity, and entropy. In this truth lies a paradox more beautiful than fiction. To look into the sky is already to look across centuries, to see the universe as it was, not as it is. Every photon that arrives on Earth is a fragment of history, proof that light itself is a time machine. The stars do not show their present, they show their past. The cosmos has always been carrying humanity through time, forward, outward, deeper into mystery. The mainstream theories had drawn their boundaries with care, grounded in experiments and equations that held firm under scrutiny. Yet, at the edges of that map lay darker waters, where speculation and imagination intertwined with mathematics, and where time itself seemed to shimmer with impossible possibilities. Here, in the fringe and the untested, humanity glimpsed shadows of futures that might never be, and of pasts that might never stay buried. Einstein's equations, though sober in their predictions, allowed strange children to be born from their mathematics, closed time-like curves. In these solutions, an object could follow a path through space-time that eventually bent back upon itself, returning to its own past. These curves were not fantasy, but legitimate geometries of general relativity, lurking in the mathematics like hidden corridors in the architecture of the universe. If such paths could exist, time would not be linear, but circular, a serpent devouring its tail. One proposal for engineering such a loop was the Tipler cylinder, a concept introduced by physicist Frank J. Tipler. Imagine a cylinder of infinite length, rotating at nearly the speed of light. According to Einstein's field equations, such an object could twist space-time into loops, permitting a traveler to journey backward in time. But the requirements were beyond comprehension: infinite size, perfect stability, and energy scales far beyond the reach of stars. The Tipler cylinder, like a mirage, stands as both a possibility and an impossibility, reminding science that not everything allowed by equations can be built by nature. Yet mathematics continues to conjure possibilities. Wormholes, already speculative as bridges across space, have been imagined as tunnels across time. If one mouth of a wormhole were accelerated close to the speed of light, or brought near a massive gravitational field, time dilation would shift its clock relative to the other mouth. A traveler stepping through could emerge not only in a distant region of space, but in a different epoch of time. The equations allow it. Reality, so far, withholds its confirmation. Quantum theory, too, whispers of temporal strangeness. Entanglement links particles across vast distances, binding their states so that measuring one instantly affects the other. Though no information travels faster than light, the correlation suggests a deeper fabric in which time and space may not be primary. Some interpretations extend this strangeness into retrocausality, the idea that present choices could influence past outcomes, that effects might ripple backward along hidden quantum pathways. In laboratory experiments of delayed choice quantum erasers, outcomes appear to retroactively alter what was decided in the past. Physicists caution against oversimplification. The mathematics remains intact, free of contradictions. Yet, to the poetic imagination, the experiments suggest that the arrow of time may not be as rigid as daily life insists. Others turn to the multiverse for answers. In this vision, every quantum event spawns branching realities. Time travel backward might not mean altering one's own past, but stepping sideways into another branch where the past is different. The paradox of killing one's ancestor dissolves if the act creates or accesses a parallel history. But the cost is profound. Identity and continuity unravel, and the traveler may find themselves not in their own history, but in a stranger's mirror. The past, in this sense, may be unreachable, forever shifting into other versions that resemble it, but are never truly the same. Each of these speculative pathways confronts the same philosophical wall: causality. If the past can be altered, does free will exist? If the universe allows loops in time, what prevents paradoxes from unraveling logic itself? Physicists propose mechanisms like the Nevikov self-consistency principle, which suggests that any action taken by a time traveler must be part of history all along. In this view, free will collapses into inevitability, and time travel becomes a dance without choice, a script already written. Others counter with the possibility of multiple histories, each consistent in itself but branching endlessly. The speculative edges of time theory are not careless fantasies. They are rigorous thought experiments, carved from equations and tested against the limits of logic. Yet they remain unanchored, unverified by experiment, suspended in a twilight realm between possibility and impossibility. They stretch human imagination as much as they stretch espact. In contemplating them, the universe reveals its most unsettling truth. Mathematics may allow structures that reality never permits. Closed time-like curves, typeless cylinders, retrocausal loops. They may exist only in the imagination of equations, never in the fabric of nature. Or perhaps they wait, hidden in corners of the cosmos yet unseen, written into the geometry of black holes or the quantum foam of the Planck scale. The journey into speculative time travel is therefore not just a scientific pursuit, but a philosophical mirror. It forces humanity to confront questions of destiny, of freedom, of the very meaning of cause and effect. If the past can be rewritten, what becomes of memory? If the future already exists, what becomes of choice? And if every path is possible in some universe, what anchors identity at all? Here, at the edge of physics, science and philosophy blur, and time itself becomes less a river than a labyrinth, with pathways forward, backward and sideways, some real, some illusory. and some forever locked behind the doors of paradox. The speculative edge of time study, though often dismissed as fantasy, continues to haunt both the scientific and philosophical imagination because it refuses to fade. For every paradox that seems to close the door, another mathematical possibility cracks it open again. The universe, in this sense, behaves like a riddle that tempts curiosity but denies resolution. Consider again the closed time-like curves hidden in the equations of relativity. They are not inventions of dreamers but natural consequences of certain solutions to Einstein's field equations. In a universe rotating on a grand scale, as Kurt Gödel once proposed, light cones could tip in such a way that paths through spacetime loop into themselves. Gödel's model was a fully valid universe under general relativity, one in which an observer could trace a path into their own past without contradiction. It was not dismissed for being mathematically flawed, but for clashing with observation. The real cosmos does not appear to rotate in such a way. Yet the model remains, reminding scientists that time's rigidity may be more fragile than intuition allows, even without cosmic rotation. Theoretical constructs, like traversable wormholes, expand the imagination further. A wormhole, stabilized by exotic matter with negative energy density, could act as both tunnel and clock. If one mouth of the wormhole experienced stronger time dilation than the other, through rapid acceleration or proximity to a massive gravitational field, a traveler could emerge having bypassed years, centuries, or even millennia. The paradox is that the tunnel itself would remain consistent with relativity, never breaking its mathematical laws. What breaks is human certainty about chronology, yet the obstacles are immense. Exotic matter, required to hold a wormhole open against collapse, has never been observed in the necessary quantities. Negative energy appears fleetingly in quantum effects, such as the Casimir force, but on scales far too small to sculpt spacetime. Mathematics smiles at the possibility. Reality so far withholds the material. It is as though nature permits the thought, but not the act, teasing the imagination with glimpses of unreachable doors. Quantum mechanics complicates the picture further. In classical physics, cause precedes effect with absolute clarity, but in the quantum world, the line blurs. Experiments in delayed choice setups have revealed that the behavior of particles, whether as waves or particles, can appear to depend on measurements made after they have already traveled. To some interpretations, this hints that present decisions can ripple backward, reshaping the past's description. Retrocausality, though controversial, sits quietly in mathematics, neither fully required nor fully forbidden. It is a reminder that time, at the smallest scales, may not flow with the straightforward inevitability that human minds expect. Entanglement only deepens the unease. When two particles are linked, their properties remain correlated no matter how far apart they drift. The act of measuring one instantaneously defines the state of the other, as if the separation in space and perhaps in time dissolves, though no usable signal passes faster than light. The phenomenon suggests that time and distance might not be as fundamental as they appear. Some thinkers imagine entanglement as a shadow of a deeper order in which past and future are not separate, but simultaneous expressions of a hidden whole. From here, speculation turns to the multiverse. If quantum events generate branching realities, then perhaps time travel is not a violation of causality at all, but a movement between parallel histories. A traveler who steps into the past may not alter their own timeline, but slide into another, one in which the past unfolds differently. In this model, paradoxes dissolve, yet, at the price of personal continuity. The past that one left behind may remain untouched, while the new past belongs to a different world entirely. Time travel becomes not a return but an exile, the crossing of a threshold from one branch of the cosmos into another that can never be reversed. This idea unsettles more than it comforts. For if every possible past and future already exists in some multiversal branch, then the sense of agency collapses. Each choice becomes not a decision but a fork in an already sprawling tree of possibilities. Free will, in this picture, may be only the illusion of moving through branches already written. The paradox of time travel transforms into the paradox of identity, which self is the traveler, and which branch truly belongs to them. Philosophy circles back with relentless questions. If closed time-like curves exist, does the universe enforce consistency, ensuring that every action taken in the past was always meant to be? The Novikov principle answers yes. History cannot be changed, only fulfilled. A time traveler who attempts to alter the past only creates the very conditions that make their journey possible. In such a cosmos, free will shrinks into inevitability, each action locked within the script of eternity. But others reject this vision, proposing instead a multiversal escape. Every alteration births a new timeline, branching reality outward like rivers splitting into countless deltas. In that view, paradoxes dissolve, but the price is endless multiplication of worlds, each as real as the next. The unresolved tension between these views mirrors humanity's broader struggle with time itself. Is the universe a block where past, present, and future coexist eternally, and time travel is simply a shift of perspective? Or is time a flowing river, unidirectional and irreversible, in which loops and detours are illusions forbidden by the deeper laws of entropy? The fringe theories do not provide final answers, but they illuminate the edges of the mystery, where science and imagination touch. Even the act of considering such possibilities reshapes the way humanity perceives its place in the cosmos. Time is no longer an unquestioned backdrop, but a fragile structure, perhaps even a negotiable one. If wormholes could exist, if entanglement whispers of connections across epochs, if retrocausality shapes the quantum dance, then the universe may harbor layers of reality that remain invisible to current eyes. Each theory, however speculative, is less a conclusion than a reminder. The universe is stranger than human logic dares admit, and so the speculative frontier remains. The Tipler cylinder, the G-Del universe, the wormhole time tunnel, the retrocausal photon, the multiversal branch, none have been observed, and perhaps none ever will. But their very existence in mathematics reveals the flexibility of the cosmos, the willingness of its equations to entertain realities beyond the everyday. They serve as cosmic parables, teaching that time is not simple, and that the ultimate machine for traversing it may already exist, hidden within the structure of reality itself. In this way, speculative theories are not mere science fiction. They are maps of the possible, drafted on the canvas of mathematics, waiting for reality to either erase them or affirm them. They challenge human certainty, destabilize the notion of cause and effect, and demand humility before the vastness of what remains unknown. For at the fringe of physics, where time bends back on itself and causality trembles, lies the profoundest question of all, not whether time travel is possible, but whether time itself is what humanity imagines it to be. In the silence of space, where human presence is absent, yet human imagination endlessly reaches, The pursuit of time itself has become a frontier as real as the planets and stars. The modern era of science has turned telescopes, detectors, and algorithms into vessels of steel or fire, but of perception tools capable of peeling back the layers of history that stretch across billions of years. What was once a myth or dream has taken the form of concrete engineering, and the very act of watching the universe has become a form of traveling into its earliest epochs. The James Webb Space Telescope, suspended 1,000,000 miles from Earth at its orbital perch, is often called humanity's most powerful time machine. Its segmented mirror, gilded in thin sheets of gold, drinks in the faintest radiation of the cosmos. Infrared light, stretched by the expansion of space-time itself, carries the signatures of stars and galaxies born just 200 million years after the Big Bang. To see such light is not to gaze across distance alone, but across time itself. In those blurred, ancient signals lies the record of cosmic dawn, the first generation of stars burning hydrogen into helium, scattering ultraviolet fire into the dark seas of primordial hydrogen. Each photon is a messenger that began its journey before Earth was even conceived, before the sun ignited, before the spiral of the Milky Way had settled into its graceful arms. The Webb telescope, by design, transforms astronomy into temporal archaeology, peeling back the epochs layer by layer until the story of beginnings comes into view. Yet, light is not the only chronicle of the universe. Gravity too carries memory. Across the dark fabric of space-time ripple gravitational waves, born in the collisions of black holes and neutron stars. These waves, first detected in 2015 by LIGO, shook the mirrors of the earthbound interferometers by less than the width of a proton. Yet their story resounded across 1 billion years of history. Now, new projects stand on the horizon. The European Space Agency's LISA mission, an immense triangular observatory formed by spacecraft separated by millions of kilometers, seeks to extend our hearing into lower frequencies. There, it will capture the murmurs of supermassive black holes spiraling together. Events so distant that their collisions predate the birth of our planet. The Einstein telescope, a vast underground facility planned in Europe, will refine the sensitivity of detection even further, turning Earth itself into an ear pressed against the whispers of the universe. These instruments do not move through time, but they let time's echoes come to us, carrying with them the fingerprints of cosmic history etched into space-time itself, at smaller scales. Laboratories on Earth probe the possibility of reshaping causality itself. Physicists experiment with entangled photons, particles born in pairs whose fates remain mysteriously intertwined no matter how far apart they drift. In certain experiments, a choice made in the present seems to affect the outcomes of measurements that from another perspective belong to the past. These strange demonstrations of quantum retrocausality remain debated. Yet they suggest that the boundaries between cause and effect may not be as rigid as human intuition demands. If time is not a river flowing in one direction, but a web of relations woven across events, then the laboratory becomes a theater where the strands of chronology can be plucked and tuned. However faintly, artificial intelligence now joins this exploration, not as a companion but as an extension of human perception. Vast sky surveys, such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time, are preparing to map billions of galaxies across billions of years. The data is far too immense for human eyes alone to process, so machine learning algorithms are trained to detect patterns, motions, and structures across the cosmic archive. Each detected cluster, filament, or void becomes a pixel in the map of time's unfolding. A reconstruction of the universe's history written not in words, but in algorithms, probability, and light. The machines that sift this data become cartographers of time itself, sketching a map across the ages that no single mind could ever hold. Even as these efforts remain focused on observation, they carry the quiet suggestion of manipulation. Telescopes stretch human sight backward in time. Detectors extend human hearing into the vibrations of creation. Algorithms grant perception across scales of complexity that once lay hidden. Each step brings humanity closer not only to watching time, but to imagining its control. The thought is almost dangerous, an echo of the myths of Icarus, who sought the sky only to be undone by his ambition. Yet it is also inevitable, for curiosity has always pressed beyond the horizon of caution. In the laboratories of quantum optics, engineers refine clocks so precise they lose only a fraction of a second over the entire age of the universe. These clocks, based on the oscillations of atoms, reveal how gravity bends the very rhythm of time. A clock set a few centimeters higher than another ticks at a slightly different rate. These subtle effects, once irrelevant, now become essential for technologies that bind the modern world: GPS satellites, banking networks, scientific synchronization. To command time with such precision, even in so humble a form, is already to step into the realm where time itself becomes a parameter to be engineered. At the intersection of technology and philosophy lies the lingering question: when will humanity cease to be a passive witness of time and begin to navigate it? For now, all efforts remain observational, constrained by the laws of physics as they are known. Yet each discovery deepens the sense that time is not a monolithic, unstoppable current, but a structure, textured and complex, with pathways that may one day be traversed. The present age may not yet command the machinery of time travel, but it has built the instruments that transform the impossible into the conceivable. As the Webb telescope watches the faint glimmers of first light, as gravitational detectors listen to the tremors of black hole mergers, as quantum laboratories hint at retrocausal whispers, humanity stands at the threshold of understanding time not as a passive backdrop, but as an active landscape. The ambition remains quiet but insistent, to move from seeing time to holding it, and one day to walking its hidden corridors. For in the unfolding of these efforts lies the most human of pursuits, the refusal to remain bound to a single fleeting moment, the yearning to step beyond the arrow of time, and to discover whether the past and the future are destinations that can one day be reached. The quest to capture time has never been confined to a single instrument or discipline. It unfolds as a symphony of parallel efforts, each with its own rhythm, yet all converging toward the same elusive goal: to decode the architecture of the cosmos and the chronology that holds it together. From orbiting observatories to buried detectors, from quantum laboratories to planetary probes, the human species is weaving an ever-expanding net to catch fragments of time's fabric in the void between planets. Spacecraft themselves become messengers of temporal discovery. Voyager 1 and Voyager 2, though launched decades ago, continue to send back whispers from interstellar space. Their instruments no longer merely measure particles and fields. They embody time on a human scale. Each transmission carries with it the delay of light years, a faint echo from the edges of the sun's dominion. To listen to Voyager today is to listen not only to distant plasma waves, but to the persistence of human intention across generations. These craft, drifting into the galactic sea, remind us that exploration is not confined to the present moment. It is a bridge across time, built by hands that will never witness its final destination. Meanwhile, the field of gravitational cartography grows ever more intricate. Scientists envision a future in which a network of detectors spans not just Earth, but space itself, an array sensitive enough to capture the faint hum of gravitational waves left over from inflation. The rapid expansion that defined the universe's first trillionth of a second. If detected, these signals would serve as the oldest observable fossils of time, echoes from an era when the universe itself was less than a heartbeat old. Such detection would not simply answer questions about origins. It would illuminate whether time itself had a beginning, or whether it emerged from a deeper, timeless sea. The efforts do not stop at grand observatories. In quiet laboratories, researchers explore the possibility of manipulating entanglement not just for communication, but for probing the temporal order of events. In certain quantum protocols, the sequence of cause and effect can be placed into superposition. One event may precede another and also follow it, depending on the experimenter's choice of measurement. These are not science fiction devices, but real, testable procedures being demonstrated with photons today. Though limited, they suggest a future in which control over the flow of information across time could move from philosophy into engineering. Artificial intelligence continues to widen the scope of what can be known. Trained on the patterns of cosmic microwave background radiation, the faint afterglow of the Big Bang, algorithms now refine cosmological models with a precision unattainable by human calculation alone. These neural networks, designed to recognize the faintest anomalies, could be the first to notice signatures of new physics, the imprint of cosmic strings, the trace of primordial gravitational waves, or the subtle distortions that hint at other universes pressing against our own. In this way, machines are not only charting the structure of the cosmos, but serving as early scouts for the deeper, temporal mysteries that lie hidden within its data. The ambitions of planetary exploration also intersect with the study of time. Missions to Mars, Europa, and Titan are not simply geological surveys. They are inquiries into the history of time as written in ice, stone, and atmosphere. Each crater, each sediment layer, each trapped bubble of ancient air tells a story of epochs long past. The search for microbial fossils on Mars is, at its heart, a quest to read the chronology of life itself.